And I'm going to start with building a legged robot with ROS. So most of you are probably familiar with this robot that we have here developed at ETH. And I want to walk a little bit through how I've been using ROS, what are the tools that we developed in order to make this run. So Animal is a four-legged robot that we initially designed to study legged locomotion. Then it turned out it's really well suited to go into rough terrain, to get the robot into difficult to reach places where other robots with wheels and tracks get stuck. So here we see Animal on an industrial oil and gas site carrying cameras to perform automated inspection of this site. There's a docking station. It has to go through rain to show it's water and dust proof. So it's meant for these harsh environments. It's fully autonomous. It localizes itself. It perceives the environment, maps obstacles, and then can plan its footholds into trajectories to overcome these obstacles. You can use the pose of the robot to change the height of the camera to reach inspection points which are hard to reach. And finally, we climb up here ladders which are difficult for other robots with the legs. These are really steep stairs or ladders above 45 degrees. So they're really tough to go up. Like I said, we carry an inspection head on the robot where we do three parts. One is the visual inspection, where we can look at gauges and valves to read them out. And we have a zoom camera to where we do localize the robot to really zoom onto these elements and do automated inspection. We use computer vision to read out the state of these elements. We have a thermal camera on board where we can from remotely measure temperature of various elements on site. And lastly, we have two different microphones to measure, to read the sound level of pumps and to also to read an ultrasound microphone to read, to check if there's any gas leaks in the environment. This is typical, which you get when you start on such a mission. You have a CAD file of the environment of the industrial site, and you get kind of like these plans, and to tell you, okay, we have here several checkpoints, and typically a person will go around with a sheet like this and check the following information. It can contain, check this lever, if it's open, check that one too. If that is closed, then proceed there. Otherwise, do these and these things. So it can be quite complex to check the entire state of the site with these different elements. So starting from this, we then take our robot Animal, which is now really designed for outdoor operation. So it's waterproofed. It can crash. If it slips, it doesn't break. It'll get up and continue to do work. It's reasonably fast, so we design it to work at 1 meters per second so we can follow a human easily. It has a modular payload up to 10 kilograms, where in this case we carry these cameras and microphones. It's safe and lightweight in the sense that it's one person can lift up the robot and deploy it easily. So it's not a 150 kilo robot that if it falls on you, it would crush you underneath. It has extreme mobility in the sense that it's a small robot, but with its legs that can fully rotate, it can overcome significant obstacles for its size. It's fully autonomous. It has in this picture a rotating laser sensor in the back and a stereo camera in the front, which uses for localization, mapping, obstacle detection, and navigation. And the battery lasts for roughly 3 hours, so we can do really a long-term mission on these sites. If you look at the PC stack, what we have inside is 3 PCs on board Animal. So everything that Animal does is within the robot, and it doesn't need a wireless connection to do so. The first one is what we call a Commotion PC, and of course, this features an interface to ROS. And what we do here, we have attached the drives, the motors for the robot. We have an IMU to measure the orientation, and we have optionally foot contact sensors. And what happens here is that the robot does the state estimation and the control in an update cycle of 500 Hertz. And it's really important here that this loop runs in real time in order to provide the stability and the locomotion skills for the robot to stay upright. And then we have a ROS interface, which we can then multi-thread to communicate with the operator and the other PCs. Another PC, what we call the navigation PC, is then concerned with the entire localization, mapping, and motion planning. And since these can take significant CPU load, we put them on a separate PC. And they communicate internally over Ethernet via ROS. Like I said, here we have attached laser sensors and navigation cameras. And lastly, we have kind of like the application PC, where somebody could implement their specific application. And in this case, we have an inspection PC, which has all the industrial inspection sensors, such as the cameras, microphones attached. And then we have computer vision and other algorithms to read out these elements and report about the site, the state of the site. Then the robot carries a wireless router, which over it communicates to the Wi-Fi of the site. And then we have an operator PC, which again runs on ROS, which features the remote control user interface and has a bunch of visualization of what is the robot currently doing, what does it see, what is it going to do next. And importantly, it creates a protocol of the site. So it tells you these and these things are within these values, these are abnormalities, etc. For safety, we have on a different channel this operated joystick, which could be used to control the robot, but if it's in autonomous mode, it's essentially only used as a remote emergency stop. So in the following, I'm going to go through these three elements, the Commotion PC, navigation, and inspection, and look a little bit at these elements and how they're implemented using ROS. Well, first, we're going to look at the Commotion PC. Here, it's really about the fast and control cycle of the robot. So reading the sensor measurements of the robot goes into a state estimator, which gives us the pose of the robot with respect to the world. Then we have a whole body control framework, which generates the gates and stabilizes the joints such that it can track the desired trajectories. These commands are then sent to the actuation, which internally has another controller which runs at multiple kilohertz in order to follow the trajectories that come from the whole body controller. And finally, the torques are applied to the robot, and we update this entire cycle for 500 hertz. We look at more closely at this whole body controller. What we have internally, how we implement it is we have a library of different modules that provide us with skills that the robot can perform when controlling it. So we have different controllers, we have reflexes, we have gate patterns, etc. And these are kind of like these abstract implementation of skills, and we can add them to different types of controllers. So for example, if we walk fast and flat ground, we can trot, use a couple of these elements in a trotting gait, or we go more carefully with the crawling gait, so only one step in the air. Or finally, we have this free gait controller, which allows us to do various maneuvers, not only walking. Here for these two, we would either use the PC or this joystick to command it on a velocity basis. And here what we've been doing is using the power of ROS, create this API, what we call here in the free gait messages, to allow the robot to perform various actions. And these are now motions that have been programmed through this API. So here we see how the robot goes over a bigger obstacle by turning its legs. It does stair climbing, it does a docking station maneuver, and jumping. And so we can very easily create through this free gait API these different motions. It's robust in the sense it's not only replaying these joint motions, but rather has a understanding of the morphology of the robot. So we can send through this API base motions in different frames, end effector motions, and joint motions. And by combining these, we can quickly create versatile and robust motions. It's implemented as a ROS action. This is what we have looked at in the last course. So when you send it a command, it will tell you this is the progress. You can stop at any time, replace it with a new action, etc. We have written frameworks for YAML. This is what you've been using for the ROS parameters. We have a Python and a C++ interface. And here's a very simple example of, a little bit hard to read, but this is the entire code that is needed to do this three-legged push-up. So in the beginning, you tell it, put your end effector this position with these coordinates, and then we have this base auto command, which generates automatically base motion based on nonlinear optimization, and we simply change the height. And since we have specified this point in the end effector as a weld frame, all the inverse kinematics and generation of the motion happens automatically. So with only a couple of lines, we can create this, flexibly create these versatile motions. We look at the navigation PC. Here's where we get this laser range data here visualized as a laser range sensor. And then we do a couple of steps, such as we need to localize, we need to map the environment, interpret the map, and to do planning on this. And we'll go through these elements. So for localization, we use a method called iterative closest point. This is given a reference map that you either given by the CAD or you recorded yourself. The robot matches the current view with this reference point cloud. And we do this by rotating this planar laser range sensor to create a full 3D point cloud shown here in color, and then match it with the reference frame. With this, the robot can localize in sub-centimeter accuracy on the site, which is very important for navigation and then also to read the elements. For mapping, we use here in this example stereo cameras in the front to also generate these point clouds, and then we fuse them in a probabilistic framework to create these elevation maps, which means essentially it's a 2D grid which at each position holds a height value. Here the interpretation is it also looks at the colors, at the quality of the footholds. So blue elements would be safe to step at, and red parts are unsafe, such as at these edges. And this framework is, if other people who have been using this on different robots, is open source, and you can use it with lasers, with Kinect, stereo cameras, Velodynes, etc. So it provides possibility to attach different sensors to it. Now, if we look at these maps, we're going to use them here, coming from these sensors, going through this mapping framework. We want to do many things with them. One thing I've shown you is this foothold scoring. So where is it safe and unsafe to step at? We want to look at the traversability. We want to visualize it. We want to do collision checks on it, etc. And here we developed a library that allows us to handle these maps in a powerful and flexible way. This is it's also open source, what we call the GripMap library, and it allows us to deal with these maps in various ways. It's efficient because it's implemented as a 2D circular buffer. It's based on Eigen. If you know that, it's a C++ linear algebra library, which allows you to do powerful linear algebra calculations. And often you're going to do things like check for a foothold, check for a polygon, do collision checking on a line, etc. So we have a bunch of convenience functions that we can use and reuse in our algorithm. And of course, it has a ROS and OpenCV interface, such as here in Arvis, we can visualize our maps nicely for debugging purposes. Now, one example to do with this map is to look at it and say, how easy is it for the robot to go through this area? So given an elevation map like this, we wanted to judge the traversability. So we're going to look at different elements. We say, okay, how high is the slope? What is the roughness in this area? And what is the step height? From these values, we can then create a weighted sum and say, okay, the blue areas are safe for the robot to go at. Over the edge, you cannot. And the ramp is somewhat difficult. Then based on this map, we can use the online mapping, interpret it online, and then do planning with it. So here we use a RRT star, which we borrow from the Open Motion Planning library in order to create this motion, this navigation path. So the robot starts at one point, and the desired goal is back here, and the robot doesn't have actually knowledge. So you see how the map builds up as it goes. In unknown areas, it assumes it can go straight, but as the robot walks, it observes obstacles, and very intuitively, it will find the quickest path through this environment by continuously mapping and replanning the path. Now, if we look at the last PC, the inspection, I'm going to walk you through one example on how we do inspection for gauges. So in the first step, you need to know where do I have to stand in order to get the best view on this inspection element. So here we have written a software which generates automatically these viewpoints, and it gives you also a quality measure on how well can you see it from this direction. So based on this, we can then select the first best guess, and if it's not visible, we just move to the next. So very intuitively, like a human, you look at from one position. If you don't see it, you try from another one. Then we can use, like I mentioned, the versatility of our robot to position the cameras up or down low, because often these elements are hidden between pipes, etc. Then since we never have a perfect localization of the element, we use visual servoing to zoom in to this gauge very precisely. Once you have that, you have to, since you probably look at it from a tilted angle, we dewarp the image, and then we can do indicator reading based on this dewarped image. So here it would tell you, okay, I have a good reading, 2 bars, and also it here works, it's very robust. It tells you, okay, I got to see this indicator, but it's also important that if it fails, it's just not giving you an arbitrary number because you think it's, okay, it's 8, because maybe this reflection tells you there's an indicator. So it has to be robust in a sense that if there's reflection or if it's missing, it tells you the reading could not be done successfully. This is what the operator sees. This is the user interface that we put together with these RQt plugins. And you have here a 3D visualization in RViz. You have a situational camera, which is kind of wide angle. And within this camera, you can then click on elements, and then the zoom camera will zoom there automatically. So it's nice if you have a point, you want to look at it, you just click on it, and the zoom camera will then give you the closer picture. Down here, we have several different modules. And what I show here is the mission control protocol, which tells you about the progress of the mission. And here's kind of like the checkpoints and mission occurrences that happen during this mission. Finally, this is debugging information, analysis about robot actuators, and sensors, the state of it. And if there's any errors on the system, it will show up here. Now, since we have been using these plugins, and if somebody only wants to do simulation and study commotion, he doesn't need to have the camera, etc. What we can do is then reshuffle these plugins and create a simpler interface, such as we have it here, where we can use this to study locomotion of the robot. So very flexibly, we can create, based on these plugins, different interfaces for the need at hand. Now, since the robot is out in the field, there's some wireless, there's interference, etc., it's always difficult to get the full bandwidth. So there's some considerations that you have to do if you have a robot with lots of sensors on it. First, you only want to send critical data, because if you send to full resolution images, it will just block the entire transmission from the wireless, and you will not get other important data. So we only send, by default, the state of the robot and its position. And if we need other things, just like a map or a video, you ask it on demand. So you enable it, and then if it's blocking, you can disable it at any time. Also importantly, we've been working with this TF topic, and this can be quite, if you have a robot with a lot of joints, can be quite intensive. So what we did here is to minimize the bandwidth of this TF topic by having a high frequency TF topic on the robot and then minimizing it, because I don't need to see it at 400 Hertz in RViz. It's good enough if I see it at 2 Hertz. So we separated the high speed TF from this TF minimal for the visualization. And finally, it's always good to see if you have good Wi-Fi connection. And for this, we developed this plugin that you can also use in your project. It's kind of like an indicator toolbar, which continuously checks the ping to the robot to see, tells you to which PC, to which robots, what kind of quality connection do you have. Here's another user interface example where we create a post graph. So this will tell you these different elements where the robot then can go through and stand on to do visual inspection. And instead of typing it into a big file, what we did here is to interactively create this tool where you can drag the robot around, set them, and load it again and edit it. So you can very quickly see if the plan that you have makes sense for the given site. once you start the mission and you execute it, and like I told you, there's going to be tasks where you have to decide on what you're going to do next based on the current state. And how we implemented this is as a state machine. And here's an image of these different states which can run in parallel and can be concatenated. Again, we can specify this in a YAML format, so it's very easy to change and adapt. And we have this common building blocks such as go there, inspect, to facilitate building these missions very quickly. And so in a typical mission, which can take an hour or two, we have set up from the sheet that normally a person would get, we can set it up within 5 to 15 minutes, 5 to 20 minutes. Now, here's a couple of more things that we learned over years with a big team on a complex robot, how we try to work with ROS and make, how to try to keep things smooth. So one of the important things is that all of your developers should have the same version of Ubuntu and ROS, so you don't have incompatibility issues. We have full version control. We work with Bitbucket or GitHub to make sure all the code is reviewed and all the changes are tracked. To kind of create conventions, this is also what you've been using. We have created this ROS Best Practices workflow where it tells you on how to use these different elements of ROS. Since ROS is so flexible, you can solve the problem in many ways, but there's better and worse. And we summarize what we think are the best ways to solve the problems on this website. We use Gazebo extensively, since we have only a few robots. It's much more convenient to debug from the desk than with the robot on site. So we have these full projects in Gazebo, and we can run entire mission fully autonomous in Gazebo before we go into the real robot. This is another important thing, that in debugging, instead of looking at the console at numbers, we try to visualize as much as possible. So here we have a view of our vis and all the elements. So you would see the velocities, the forces, the friction cones, etc. And the human is very good at picking up problems. So if suddenly this cone will be over here, it will be hard to notice in the console, but it's very easy to see by eye if something's wrong. Although we use Gazebo, it's always important to do lots of tests on a robot. And what we do is kind of like once a week, we do go through a set of tasks that the robot just has to do and that we check with a checklist just to make sure that it can still perform all the tasks, although we have been programming for an entire week. And of course, we do lots of demos with the robot. You might have seen one of those. Also, demos are also a good way to like debug your system continuously. This is interesting. We use continuous integration. We've set up this screen in the lab where each repository is a field here, and internally it has unit tests. So it tells its method itself if they're doing what they're supposed to do. And on the screen, after every change that you do, these tests are run through, and it would very quickly indicate you via email, but also via the screen if something is out of the expected behavior. During night, the robot runs through an entire sequence of motions. So here's kind of like an integration test for all the things that go together. As you can imagine, to do these motions, you need the entire simulation needs to run, you need the state estimator, you need the controller, you need the APIs, etc. It's kind of like a full end-to-end test, and you want to check for its expected behavior. You randomize it, you drop the robot to different orientations, and just tell it run straight. And you might be surprised how many times it happens that if the robot turns 180 degrees, it's not able to run because somebody forgot how to deal with the signs, etc. So these are important elements to keep things smooth. And finally, we do a lot of ROS packs, where on the robot, if we do experiments, we log the entire state, almost the entire state of the robot, such that in hindsight, we can analyze it step by step. Especially if something goes wrong, you want to make sure you have as much data as possible. And with this tool that we also showed you with this multiplot, you can then go in time very slowly through the data and analyze what went wrong. With that, I'm at the end of this part, and I'm happy to answer any questions that you have.